what we will be doing this morning is we will be doing some very quick explanation, discussing the electronic aspect of your work and then the programming aspects. The project in question is a Fetal Heart Beat Monitor. So the project Heart rate. Heart rate monitor. So the essence of the project is to first, of course, if we have to go by the definition of what we have on board, we say fetal will be it's called fetal, sorry. Of thank you. We have a medical person in the house. Thank you. How do you spell?
F-O-E-T-U-S.
Okay, thank you. So fetus. So that would be a baby in the womb still undergoing growth, or development. Okay, so we are looking at designing a system, a digital system with which a user can actually measure the heart rate of a baby in the womb. There are many, I believe, of course, you must have done all your research. There are several ways to go about doing that. But what we intend to use here is first, let me do that this now. Let me be like the students. Okay, so for this class, or for this project, we need power supply. We need a microcontroller. We need a display. Then we are going to need a microphone. The microphone should go through a preamp stage, and then from the preamp stage it should go into a filter, and then from the filter it should feed the microcontroller. Power supply should be made available to the display in question, made available to so power supply is made available to all of the blocks needed to complete the project. So here's the block diagram. You have power supply, you have a display unit, you have the microcontroller itself, you have a microphone, a condenser microphone, and then you have the preamp stage, and then you have the filter stage before it goes into the microcontroller. So this is basically what the block diagram is. So the essence of the microphone, let me do a quick introduction here, or more introduction here. For this system to actually work, or for this system to run, it's going to need to come on. One of the reasons it's going to need power is because the constituents of this project are both passive and active components. And for active and passive components, for them to be useful, for them to work, they will need power supply. Every system design will need power supply. Your wristwatch has a battery with which it comes on with, and every electronic gadget you are actually going to be making use of will need power supply. So that is why we're going to need a power supply. When the reading is gotten, you would need a means through which you can actually make sense of what is read. If the pulses are gotten, there needs to be a way to actually have it interpreted to you. The best way to have it interpreted is to have it displayed to you, to us. What kind of display we'll be using will be determined as we progress in this introduction. Now, for the heartbeats or for the heart rate to be picked up, you are actually going to need a microphone. The essence of the microphone is such that the beats coming or the sound being made by the baby or by the fetus in the womb can be picked up, and then because of the nature of the signal, it could be weak. The output from the condenser microphone itself could be so weak such that we cannot directly have it fed into the microcontroller. It's why we're actually sending it through a preamplification stage. The essence of the preamplification stage is just to actually double it. In audio amplification, what we simply do is to multiply the output by a ratio or by a value. You can have a by 10 amplifier system, so that irrespective of what is coming out from here, it's just multiplied by a ratio of 10. That value 10 is what is then fed into the filter before it goes into the microcontroller. Now, the essence of the filter is such that because, and this is very important, because what will be amplified, the signal from the microphone into the preamplification stage will be both noise, surrounding noise, and any sound it's picking up is what is going to be getting here. The essence of this filter is to help us remove any signal outside 200 Hz. That's the essence. Let me put it down. Outside 200 Hz, which will be the frequency bandwidth or the frequency range in which the human voice or sound made by woman can resonate in. The microphone will receive everything. The preamp stage will amplify everything this man is receiving. The filter is just there to help us sieve out some sound outside this range, so that what we now have will be every other thing below or within the range set by the filter. Are you there? And then before it then fed into the controller then does all of the manipulation. But again, this is another thing I want you to understand, which is what the manipulation I was trying to do before you came in. Even after the filter, what the filter just simply does is remove the overriding noise or noise outside a particular range, removes it. What is still being fed into the controller is still every sound that is gotten. It means that the onus is then on us to see as much as possible to block external sound, so that the only thing that this microphone will have to receive will be the sound that is being produced by the fetus through the womb, or through any means, or through the womb or the stomach where the mic will be placed. Now, for a woman that has whose stomach makes noise, don't forget the fetus itself is far inside. Of course, it's going to be maybe in a membrane with liquid, and then the inside the womb, and then you have the woman's stomach and every other thing that covers. Apparently, it will mean that for the noise to be received at all, this microphone first must have very, very high level of sensitivity, which of course will mean that it could also pick up noise, overriding noises, and when it is amplified, you have more noise amplified. The filter just helps us cut that frequency outside the 200 Hz range and then give that to us. The question is, how then do we separate the pulse that the baby is having plus the noise made in the stomach? If the baby is in the womb and is turning or is moving or is stretching, you're going to get sound being made. We have people with quite a lot of warmth in the stomach that makes noise. So how do you sieve out the pulse or from noise? How do you now get out the pulse? That is actually what I'm actually trying to figure out. There needs to be a way, unless we can actually say maybe after this filter, send this sound again into another system that can help us digitalize it. But if it digitalizes this for us, then it has done the work for us. What I'm trying to say in essence is this: whatever I'm going to be explaining now is how your project is supposed to be, but it will not stop you from actually manipulating the hardware, bringing other things in to have a result. And I'm so glad you've been able to give me that number of weeks to do that, and then the privilege to do so. Because the truth is, what will still be received by this man will still be everything that is being said. How you now convert that to pulse is a different kettle of fish. And that is something we still need to figure out. Because if I filter the noise, okay, the noise has been filtered. What we are still getting are just a digital representation, or will just be digital representation of what the sound is getting. And that is still not pulse. That's why the last time I told you we are getting values. Different value ranges depending on the noise that are being used. But those are not pulses. And if we decide to read, say, every single value, say maybe in every second, what it means that we have determined in by ourselves to say that that baby will give only a pulse in a second. If we are reading only the sound every second, or we are reading every second sound for 30 seconds or for 60 seconds, and then we are adding them together and getting the main value, our controller inserts parallel. That is not what the baby is actually doing. If we say, okay, let's pick every 1 microsecond sound and find how many microseconds we find in 60 seconds, because of course, don't forget, the unit of our result is going to be in bits per minute. And bits per minute will be we need to read those pulses for 60 seconds to be able to have an accurate answer. If we read for 30 seconds, our result has to be multiplied by 2. Are you following me? If we read for less than that, we need to find the division or the ratio or the multiplier to get 60 and multiply by that value we've got. But yet, our line is set in scenario. That scenario needs to be set not by us, but by the system. But because of the nature of the microphone we are using, it will be difficult to set that unless we bring in other components. So I'm saying this such that when I come back with a different circuit diagram, why you do not need to attach that to your supervisor, you can still give them this, because this is what is consistent on the internet with using a microphone. Alternatively, if I get a system that just counts pulse, all it does is to count pulse and give to me the amount of pulse it has counted in 60 seconds, it's still going to do the project or do the job, as against gathering every sound possible and then seeing how to actually break those sounds into every pulse. Do you get the point now? That's what I'm saying now. Because what the microphone will be giving, if the microphone was a horn right now, what it will be receiving the alternation, AC signal alternates. So the signals, of course, don't forget, for it to actually even go into the mic, the DC property in my voice has to be blocked by its capacitors already in the preamp stage and the filter stage, so that only the AC property of in my sound or in my voice or in my speech is what is received. How then do we convert that to pulse? It's still something we still need to work. So I need to say that for the record, so that we're on the same page. Alright, but all things being equal, assuming that after the mic it picks up the sound, it goes into the preamp stage, it is filtered, you get pulse. Those pulses are counted by the microcontroller. It's counted. The result of the count is what is then sent into a display, and then we have a result. Now, these are blocks. Let's now discuss the constituent materials or component that makes up each of these blocks, one after the other. And then at the end of the day, we'll say, oh, we now have been able to explain our circuit diagram, and then we can then talk about the programming that will happen. Let's take the power supply for instance. First of all, to discuss power supply, you need to know what that power supply will be powering. Okay. And you need to know the power requirement of all of the other components to determine what your power supply will be. This is what I mean. For the display we are going to be using, we had agreed that we want to write on an alphanumeric LCD. LCD will be liquid crystal display. That display requires 5 volt DC to operate. The microphone requires 5 volt DC to operate. So also is the preamp and then the filter stage. 1, 2, 3, 4, including the microcontroller itself requires 5 volt to operate. So if I'm to design a power supply, therefore, my power supply should be such that should not deliver to me more than 5 volts. Yes, don't answer it. Okay. More than 5 volts. If it does, power supply should be such that should not deliver to me or give to me more than 5 volts DC. But how do we design or come about a power supply that will do this for us? Hope you have the block diagram ready.
Yeah.
Okay. So the strong power supply that will give to us, we want a system that is portable, a system that allows us mobility with such that it can be used even when there is no light. What it means is that that system is supposed to have a battery inbuilt. The battery should be such that it's chargeable, and then when the system is not in use, it can be charged. When the system is then to be used, it can be unplugged, and then the battery inside can then be used. That's the idea. So if we are to do that, please look up. It means first is that we are going to have we have an adapter. The adapter goes into the charging circuit. In the charging circuit is supposed to be a battery. Are you following me? Now it's supposed to be a battery. It is the output of that battery that is then fed into our system. Now, the charger we have adopted to use is supposed to give to us 5 volt DC. Because we are actually using the USB. Even though that is also likely going to change. And I will explain to you. Let me explain that quickly before I come back to this charging circuit. If this was your system, requiring positive and negative, and it requires 5 volts to operate. If I go to the market and I get a battery, and my battery is 5 volts too, and I have the positive here, I have the negative here. If I connect the positive of this battery to the positive of my system, and I connect the negative of my system to the negative of the battery, what happens is that the moment this system starts running, it starts to drain this battery. Now, the moment the battery goes from 5 volts to 4.9, this system begins to misbehave. Because this system is supposed to be operated at 5 volts constant. Now, the battery level is beginning to decrease. The voltage level is beginning to decrease. That will affect the perfect or the proper working condition of the system. So, I will not go to the market to go and get a 5 volt supply to power a 5 volt system. Are you following me? What I would likely do is to go to the market and get a 9 volt battery. And get what? A 9 volt battery. My 9 volt battery, we then have to go through first a power switch. I have to go through a switch. That switch, the output of that switch, let me draw the switch here, this one. The output of that switch can then go into something called a voltage regulator. Called a voltage regulator. That voltage regulator output is what I'm now going to feed into my system while the negative comes into the supply. So this is what happens. What the voltage regulator does for you is that irrespective of the input voltage, it continues to give you a regulated output 5 volts supply, 5 volts, 5 volts. Irrespective of the input. If the input is equal to 12 volts, the output of this 5 volts will remain 5 volts. Now, the only reason or the only time when this voltage regulator will not give you 5 volts again is when the input voltage here is also either equal to 5 or less than 5. At that point in time, this one will not have anything to give, or less than 5 volts to give. You know why? Because it is not a voltage amplifier, it's a voltage regulator. It just gives you a regulated fixed output voltage irrespective of the fluctuation on the input. Is it clear? Now, so this would have been the best approach to solving this problem. One other thing I didn't have, at the output of this voltage regulator is going to be a capacitor, an electrolytic capacitor. At the input of this voltage regulator will be another electrolytic capacitor. Now, you ask again, Shebi, the battery is giving me a pure output voltage, Shebi DC. What is the capacitor doing here? Yes, the capacitor is used to filter the line, to filter the signal on the voltage line. But why will you need a capacitor to filter a DC voltage again? Shebi DC voltage is supposed to be smooth. It's not as why are you filtering it again? Yes, I'll explain that to you. The reason for the filtration is because of this switch, don't worry. Most times when you latch a switch or when you flip a switch, it doesn't close immediately you flip it close. Because mechanical contact don't want to. So they just don't connect. Sometimes it bounces before it closes. And that bounce can create electrical spike. Very little electrical spike that, if not taken care of, over time will damage this voltage regulator. So what we do is that we use this capacitor to filter that spike off before it gets into the input of the voltage regulator. That's one. The value of the ceramic of the crystal of the electronic capacitor you're going to use here is going to be 1000 microfarad, 25 volts. The value you are going to use here will be 100 microfarad, 16 volts. The question again is, why do I need capacitor at the output again? The reason you need capacitor at the output also is because the voltage in question has gone through some transformation. A 9 volt voltage has gone through, it has gone through some transformation such that now you are getting 5 volts. Wherever ripple that has resulted in, or wherever spike that has resulted in that transformation will be taken care of by this capacitor. That's why you have a capacitor at the input, and then you have a capacitor at the output. So back to the circuit diagram we're drawing. If we have an adapter, we have a charging circuit, and we have a battery. Our battery, therefore, should not be, are you with me? Yeah. Should not be just a 5 volt battery, should be a 9 volt battery. Does it make sense? Yeah. So which means from this point, the charger goes into the battery. So whether the flip is closed or open, as long as this adapter is in light, into this charging circuit, this battery is being charged.
The adapter must be 5 volts.
Now, the adapter usually should be more than 5 volts, which was what was happening when you came and you met that previous project on Thursday. The output of the adapter is low. The output of the adapter is 5 volts. The battery there is above 5 volts. There is no way that adapter will have been able to charge that battery above its own rated voltage, because 5 volts in the adapter only give. The only way that voltage can be pushed up is if that battery was charged with a 12 volt supply first, so that attain full charge. If you now bring in a 5 volt charger, what the 5 volt charger will just do is just go to the top of the voltage so it can remain there. If you drain the battery, that charger will not charge the battery above its rated voltage. That is why at the end of the day, there's a likelihood that we are going to yank off that adapter, because the adapter can only take between 5 volts to 8 volts. The charging circuit can take it between 5 volts to 8 volts. If it was taking 8 volts, or if 8 volts was what we fed inside it, it would have been easy for it to quickly charge that battery, because that battery is actually above 5 volts. That battery is actually, I think it's 4 points, that battery is 8 point something volts. 8 point something volts. I think it's 3.7, which is 7.4 volts. So at 8 volts from this charger, you have charged this battery. But since the charger itself is bringing out 5 volts, the adapter inside it is 5 volts, the battery is 7 point something volts. How then do you expect the 5 volts to charge the 7 point something volts? Do you understand that? Unless this battery has been externally charged before, that is when the charger can then be helping it to top it. You get the point? So, but understand that for your system to work, which is some of the modifications you will likely have to use. First is that this adapter will have to be more than just a 5 volt adapter. If it's nothing at all, it should be either a 9 volt adapter or a 12 volt adapter. That adapter is what goes into a 12 volt charging circuit that charges the battery. So the battery here could likely be 12 volt or 9 volt or above 9 volt, which will be 12 volt. That voltage is what is then fed through a switch into the input of your voltage regulator. Don't forget, this is the input of your voltage regulator, and this is the output. This line is the common because this is what comes to ground. It is common to both the inputs and common to both outputs. Are you following me now? So this is what your power supply circuitry will likely be. Now, this 5 volt system that I drew here will be your what? The system. Because don't forget, every aspect of the system requires what? 5 volts. So this clear? You understand this? Can I clear? So that is in explaining the power supply. Now, another person that should be explained quickly should be the display. Let me explain that display to you quickly. The display we are actually using will be an LCD display. It's a liquid crystal display. Liquid crystal display. Now, the liquid crystal display we are using is a 16 by 2. 16 by 2, which means it has 16. It has 2 lines and it can accommodate 16 characters. Characters will be alphabet and numbers and special characters or special symbols. But it will not be able to accommodate more than 16. Why it has 2 lines? Which means you can write on 2 lines. You can write on either line. You can write on line 1 and not write on line 2. You can write on line 2 and not write on line 1. And you can write on both line 1 and line 2. Now, for the microcontroller to connect to the display, first of all is that you should know that that LCD display has 16 lines itself. That's 16 wires or 16 pins. Thank you very much. That's 16 pins. So let me give you those pin assignments. P1 is VSS, followed by your VDD, followed by your VE, followed by your ROS, your RW, the AM, the DO, D1, D2, D3, D4, D5, D6, D7, A, and K. So that will be 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's 16 pins. Now, the VSS is where you put the negative of your battery or your negative of your supply. Now, don't forget that our supply looks something this way. Don't forget what it was. We had an input into a voltage regulator. Don't forget it was fetal. This was also fetal. And then you had your plus 5 volts here. So this becomes your VDD, your plus 5 volts. And this side or this point is your VSS. You call it VSS or your ground. Call it VSS or ground. Now,
The negative side.
which is the negative of your supply. Now, your VSS, the first pin on the LCD, goes to the negative side of your supply. So which means in using this, I'm going to connect this guy to this place. Now, the VDD comes in. Does it make sense? So that has taken care of the first 2 pins. Now you consider. Now let me take the last 2 pins before we take the rest of it. Now, this last 2 pin is your backlight. Now, the LCD display has a backlight. The essence of that backlight, or what's in that backlight, LED, no one backlight today. What I say is there. A light emitting diode. A light emitting diode will look this way. This is the anode, this is the cathode. Now look up. So what is behind that display that we call the backlight is just a light emitting diode. Light emitting diode because it gives out light. Can I continue?
Yes, you
Because it brings out light. Now, please go. So the anode is called the A, the cathode side is called the K. Now, for this light emitting diode to come on, voltage needs to be sent into the anode. Voltage needs to be sent to the anode. For voltage to go through the anode, what we did was the voltage. Now, we didn't just impress 5 volts at the anode of the light emitting diode. Of course, it's going to come on, but we don't want to give it that much voltage either. So what we did was that from your anode, from your VDD, we had a resistor that went into the anode. This is an 100 ohms resistor. So 100 ohm resistor from your VDD connected to what? To the anode. While the cathode came back and connected to the what? To your VSS. That was how we eliminated 1, 2, 3, 4. Another person that was also eliminated quickly, or that we should eliminate quickly, will be the VE. This VE will be your contrast control. Your contrast control. Now, you know what the contrast control is? If you had used this analog television, you know, or even your phone, you know, you can also brighten your screen such to the point where the character has been displayed will not be seen properly because of the brightness. It becomes either too white, when you turn it the other way, or it becomes too dark. You don't see it much on phone, you see it on television as contrast control, any of those, or in cathode ray tube that's contrast control. Something I didn't see, and I need to say this one. For the A and K, which is the backlight, if you don't on the backlight, it does not mean this display will not display, or you will not see what is being displayed. You might see it in the afternoon, because don't forget there's going to be a fresh light, light or sunlight that you will twitch, hit the screen, and then you can see what is written on the screen. But when it becomes dark, you won't see what is displaying, even though it is displaying something. Are you following now? So that is the essence of this backlight. The backlight does not stop the working or the functioning of the LCD.
Is it possible
for it to be disabled? Yeah, we can.
For it to be disabled, like if it gets burnt. If the AK gets burnt, is it possible to change it? If it gets burnt.
Okay, the resistor. This resistor.
Not the resistor. The AK. So it consists of LED.
Now, don't forget that AK is just no. When I mean AK, that is the name of a pin, anode and cathode. So it's LED. Say the LED. The LED does not get burnt. No, it doesn't get burnt. I've never used an LCD in my over 16 years and find the backlight get damaged. Even if you give it 5 volts directly, it won't be a problem. The only issue is that when you give it 5 volts directly, it becomes more of a load on your battery, on your supply. So to limit the amount of voltage and current or signal that flows to that anode is why you have this 100 ohm resistor. Can I continue? Now, excuse me. Now, so another person I was talking on was the contrast control. I said what the contrast control does, which of course is the VMP, is to help you set to a minimum range the level of intensity with which you can see what is being written. Now, to create the contrast control, what we simply do is to have a variable resistor between your anode and your cathode while the control goes to the V. What I meant is that from your anode, from your VDD, one end of the variable resistor is there to the VSS, while the control goes out and feeds the VDD. Now, this is a resistor.
But you know that the VDD is connected to the power supply.
Yes.
That's natural.
Yes.
Okay.
And then the VSS. So there is a resistor across it, across the VDD and the VSS. Now let me explain the difference between this and this. When I said resistor, this is a resistor. This is also a resistor. Except that this time, this is a 1 kilo ohm resistor. This is an 100 ohm resistor. And that's what you should know. This is a fixed value resistor. It means its resistance does not change. When you buy it, exactly the way it has come is how it's going to be until it gets damaged. But you see, for this variable resistor, it has a knob where you can turn. So it offers you this variable option. It means that you can vary this resistor to 1 ohm, between 1 ohm and what? 1 kilo ohms. Thank you very much. So you can vary it. So instead of having a resistor, a permanent resistor here, say across either your VADD to your V or your VSS to your V, what we do have is a variable resistor whose control we can turn to vary voltage supply to the V. Now let me even say it straight. What this V really requires is ground. It's more of ground than VDD. It requires VSS. But if you give it the VSS directly, it becomes too much for it. So what you actually vary is the amount of VSS that it gets. Okay? An amount of VSS that it gets, or an amount of VSS is what you actually vary. Not so much as VDD. So clear? So you have the variable resistor across your VDD and VSS, and then the control goes to your V. So that as you turn the knob, you can set the contrast level yourself. So if you look at it, you are taking out VDD, VSS, VDD, VE, anode, and cathode. Does this make sense? Can I continue?
Yes.
So I'm going to clean those ones off so that we can have a space to actually explain all this. So we'll discuss this. And then we have also discussed this. Now, so we are left with what? Our ROS, RW, EN, GO, G1, G2, G3, G4, G5, G6. Okay, let me explain. Let me explain. What I'm going to group this into two. Please look up. I will group this into one and then group this into another. The ROS, RW, and the EN, see them as your control pins. See the DO to the D7 as your data pin. What it means is that this is where information, characters that you plan to have displayed on the screen, this is where they are sent to, between DO and D7. Your ROS RWE is where you set controls, set how it is displayed, when it is displayed, and what it does, other things it does. For instance, you just don't send characters or you just don't send characters to the display line. Before you send characters to the display line, you need to tell the LCD, please move your cursor to this point. Clear what was there before. I want to write something new. Okay, go from line 1 to line 2. Or don't put that thing on line 2, go and put it on line 1. Or blink before you display. Are you with me? All those control command are sent through the control pins. While to display characters, those information that needs to be displayed are then sent through the data pin. Now, for you to actually use the data pin, you are going to need 8 lines from your microcontroller, which means each of these 0 to D7 will connect to this microcontroller for. Don't write it. Don't write this on it. 8 lines will be connected, will go from your LCD to your microcontroller for this microcontroller to display. But that's too much. What we've not done is that you can actually use just 4 of the data lines to write a microcontroller still. See the 8 as the parallel communication. See the 4 as the serial communication. Are you following now? Because the 4 is going to be half of the serial, of the parallel. But the implication is that for you to then display, you have to send in your data twice. Usually, if you use the 8 pins available, you will have actually sent your data just once. But if now that you are using the only 4 of it, you are then going to send your data once, twice. What I'm trying to say is that on the data lines, we do not use DO to D3. We only make your what? D4 to D7. So D4 to D7 happens to be our what? Our data line. That is the 4 lines that connect to the microcontroller where data, characters, is sent from the microcontroller to the display. Please, does it make sense? D4 to what? To D7. Now, we also need this ROS, RW, and EN connected to the controller. So that at the end of the day, instead of having 11 pins from the LCD to the microcontroller, or from the microcontroller to the LCD, we now have just 4 plus 3, which is what? 7. So we have eliminated 4 for data. So this ROS is same thing as your what? Sense reset. Your RW is your read or write. Why this your EN is your enable display. Enable display. You clear?
RW. RW.
ROS is the set reset. Your RW is a read write.
Read write.
Yes. Why your EN is the enable display. Let me just explain them quickly or briefly. Now, the LCD, for the LCD or on the LCD, you can read to the screen and you can write to the screen and you can read from the screen. But if you know, what we have actually been doing is we have been writing to it. We've not been reading from it. So we have not been taking advantage of the what? Of the read function. We have only been writing. To write to it, you need to set that pin to a 1 or to a high. To read from it, you set the pin to a 0 or a low or a high. When you hear the word high or low in digital electronics, what we are saying is that for the high, you bring in a 5 volt supply there. For the low, you bring in your VSS. Does it make sense? So that's when you hear the word high or low, 1 or 0 in data terms, what we are simply saying is bring your VDD to that pin and bring your VSS to that pin. So because we are not carrying out the read operation, we are only writing to the LCD, the state of this read drive will always be what? 0. Which means if you measure the voltage between this read drive to ground or to VSS, you are going to measure the 0 volts. But if we're reading from it, at the point of reading, we will tell the controller, please change the state of that pin to a high. So 5 volts will be impressed there, so that the LCD knows that, oh, you want to read from me. But because that pin is always kept at 0, the LCD understand that you only want to what? Give to. You're not taking from me, you're giving to. Does it make sense? So that is what this read write pin does. Because I've explained it, I'll get it out of the way. The enable, the EN is where you enable the display. Now, if this place is not high, to enable the display, it also has to be a 1 or a high. To disable the display, just make it a 0 or a low. Does it make sense? Make it a 0 or a low. But now, the question you then ask me is this. At what point should I enable the display or disable the display? I'll tell you quickly. Please look. At the time when you are actually setting controls, when you are giving it commands like clear the screen, commands like go to line 1, commands like go to line 2, and every other commands that you are giving to it. At the stage or at the point where you are doing so, this enable display is off, 0. It is at the point when you now want to have it, you have sent in your character, you now want those characters displayed, is when you make it what? High. And then the character is displayed. Does it make sense? You get it? Okay. Then for the set reset, the pin, the state of this pin will start going from set to reset. On the set, it's a high. On the reset, it's a 0, 2. So at the point of issuing command, let me just say this quickly. For both the ROS, the ROW, and the EA, while you are moving from command mode, are you with me now? While you are issuing command, and while you are actually issuing your data or the signal you intend to display, the state of these pins will be changing from 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1, 1 to 0. While your data line 2 will do what? We are having the characters that it should have. So that is the relationship between the ROS, ROW, EA, D4, D5, D6, and D7. Does it make sense? So you understand right now that apart from your power supply, feeding some pin on your microcontroller, we will not discuss that yet, we'll get to that. Feeding some pin on the microcontroller, 7 pin from the microcontroller, 1, 2, 3, 4, 5, 6, 7, will go to your LCD display. While the LCD is going to have VSS both on the anode, on the cathode, and on the K, or the VSS and on the K, is going to have VDD on the anode, on the VDD pin, and then through a resistor to the backlight, and then a contrast control to the VE. We don't make use of the DO, D1, D2, and D3. Please ignore. That's not about the display. I just thought I should discuss that quickly. Let me also discuss on the microcontroller quickly. The microcontroller that you are using, the controller that you are using is the PIC 16F8760. It's a 28 pin IC. Nice, it should look something like this. So you have pin 1 to pin 9 to pin 14, you have pin 15 to pin 28. So simple assembly. So 15, 16, 17, 18, 20, 21. Alright. So you have pin 1 now to pin 7 to pin 14 to pin 15 to pin 21 to pin 20. Does that make sense? The microcontroller you're actually using is the PIC 16F8760. It's a 28 pin IC. Now, understand that it's a digital IC, and for every digital IC, it is going to require power to come on. Now, on this particular IC, it requires, or for this microcontroller to actually even be used at all, it requires first, let me explain this numbering. I just wanted you to see how it is numbered. It is numbered from your left down to your right and then up. Okay. So I'll just know that it goes this way. 1, 28 or 28 goes this way. Now for this microcontroller to come on, it has a pin called the VDD pin. This VDD pin will be given or will be connected to your 5-volt supply line. It has another pin called the VSS. That one will be given to the what? To the ground or VSS of your supply. It's key. It has another pin called the MCLR. The MCLR stands for Master Clear Reset. Don't forget it. The MCLR is Master Clear Reset. That Master Clear Reset has to be taken through a resistor to your supply. Also, I does not confuse you. Let me see, taking the VDD. The value of the resistor that needs to be there is going to be a 10 kilo ohm resistor. Now, you need to, it has to be tied this way for it to work. Now, another thing that this controller has, or that it requires, it has this other two pin called OSC1 and OSC2. This OSC1 and OSC2 is where the oscillator sits.
That's the way you're numbering it.
No, it's not the way. No. I'm not numbering it. I'm just explaining the first important pins that are actually on the IC. But I can try with the number.
No.
Your pin 1 is going to be your master clear reset. Your pin 20 is going to be your VDD. Your pin 19 and pin 8 is going to be your VSS. Now I can't remember what these two pins are.
VSS has 2 pins.
Yes, it has 2 VSS on pin 8 and on pin 19. But on your pin 1 is your master clear reset. On your pin 20 is your VDD. Let me check for where the master clear reset is. Since you're asking.
Don't worry, I'll check it online. Let's continue with this.
Yeah, so that's going to be your
You
pin 9.
actually have to change.
So this is going to be on your pin 9 and 10. So those are,
Are they connected together?
yes, look at the way they are connected. Look at it. It's connected to a crystal oscillatory capacitor. This, yes, is a 4 megahertz crystal oscillatory capacitor. Then you have this other ceramic capacitor. This is 22 picofarad. 22 picofarad. These two are ceramic capacitors. So let me explain. You know, just the way everyone has an heart.
How did you write for that? What is the rating of that crystal electrical capacitor?
4 megahertz. 4
Why is it in hertz?
Okay, I will explain. Can I continue? Now, just like you have human being with the heart, the controller also needs something that can generate heart pulses for it. Now, such that every instruction it executes is executed based on every heart pulse it gets. You know, you can stop your heart from beating and you are still going to move. But for the controller, the moment the pulse stops, then it stops there too. Are you following me? So it requires this crystal oscillatory capacitor to generate for it that timing or that pulsing. Now, the crystal oscillatory capacitor cannot start by itself. Are you following me?
Yes.
The crystal oscillatory capacitor cannot start by itself. It requires these two ceramic capacitors to start it before it now takes charge of its responsibility. It's like this lister where you require somebody to put in the iron and then propel it. When it propels and then it starts to work. You start this big generator. So also is what this two starting capacitor is offering this crystal oscillatory capacitor. Now please look, this is key. Both the crystal oscillatory capacitor and these ceramic capacitors are examples of non-polarized capacitors. They're not polarized. They are examples of non-polarized capacitors. The issue here is that why frequency is written on this one, on the crystal oscillator capacitor, capacitance is what is written on the ceramic. Thirdly, or to answer the question you asked, why is frequency written on it? I'll explain. For the microcontroller to operate, each instruction is executed at a particular frequency or at a frequency rate. Each instruction. When I mean each instruction, I'm going to mean each single cycle instruction. is executed at a certain rate. That rate is defined by what you put here. Now, because, can I continue? Oh wait, okay. It requires, now the value of each electric capacitor that you're using affects how this man processes every code that you write to it. I'll give you an example, for instance. For every piece of electric capacitor that you use, the microcontroller uses 1/4 of that to execute its instruction. So because you have 4 megahertz crystal here, the microcontroller takes 1/4 of 4 megahertz. That is going to be 1, which is what? 1 megahertz. So the rate at which each single cycle instruction is executed is 1 megahertz. Okay. If you find the inverse of 1 megahertz, you're going to get 0.12345 such that if you do 1, 2, 3, 4, 5, 6, you're going to get 1 microsecond. Which means each single cycle instruction is executed at 1 microsecond. What it means is that this system will execute 1,000,000 single cycle instructions in a second. That's fast. That is the essence of the crystal electric capacitor. 1/4 whatever value that is there is what the system uses to execute single cycle instructions. Any instruction that is now more than single cycle instruction is multiplied, this value is then multiplied by the number of cycles. So if it's 2 cycle instruction, then it's 2 microseconds for that instruction. If that instruction is a 4 cycle instruction, then that's 4 microseconds for that instruction. Does it make sense? So to operate this microcontroller appropriately, it is important that you give it VDD, connect the pin 20 to your plus 5 volt, connect the pin 1 through a 10 resistor to your 5 volt, connect your pin 8 and pin 19 to the ground of your supply, and then connect your pin 9 and 10 in this fashion through a piece of electric capacitor with 2 standing ceramic capacitors 22 megahertz to ground. 22 picofarad to ground. Does it make sense? So this is the initial setup.
Okay, so it's not connected to the ground?
Yeah, it's connected to ground. This end, not connected to the ground. Does it make sense? Now, can I continue? Now, before I clean this up, let me just clear this out. Now, I told you that the microcontroller also sits your LCD. I mean, now your LCD, if this was your LCD, now I just want to highlight the pins that we use. Understand that if it has VSS, VDD, V, let's call A and K. You understand that this is supposed to go to your supply, the ground of your supply. So please look at it. So this is coming here. You see it? This is supposed to go here. Did you see it? This is supposed to go through a resistor in this place. You see it? And then this is supposed to come here. Do you get it now?
Okay. That means the negative is not connected to the capacitor. It's connected directly to the ground.
Yes, now the anode is connected to ground. Don't forget
the
this
cathode.
Yes.
The cathode is connected directly to ground.
Yes, now to
While
ground.
anode is connected through a resistor
to your
the
VDD.
positive.
Yes.
Okay.
But don't forget that at the output of your supply, please don't forget this. In, out, there's already a capacitor already.
Okay, yeah.
Have you? There's a capacitor at the capacitor. So this is the ground. This is the VDD.
Yeah.
So all those guys that are VDD are connected to this place. All the guys that are VSS are connected like this. While the VDD guys are connected something like this. Do you get it? Do you get the point? Yeah. So they are connected. So that's why I started with the supply first, and then went here before I came in. So when I say VDD, that's connected to all of them are coming to this point. The way the wire will then run is what differs. You go through different routes, but eventually we don't worry. and for the ground, don't borrow. So this is how you start. Now, as one other person we didn't do. Don't forget, there is a variable resistor here. That variable resistor will go from here to what? To your V. Do you get it now? So from your V, it comes to your controller. So when you pick up that circuit diagram that I sent you again and you look at it, it makes sense. Then you look, okay, why I hear it. Do you understand? So this is satisfying this particular condition. Do you want to write it or can I clean it? I can clean it. What is it? Oh. Now, look at this now. So we are left with what? Arrow is arrow W, here, D4, D5, D6, D7, D7. So, and they are connected to the power controller. Now they are connected in such a way you have 22, okay, so you have pin 21, 22, 23, 24, 25, 26, 27, and then 28. So I is connected. I'll show you. Now, this man is connected here. Followed by this man. Followed by this man. Followed by this man. This is connected. This is connected. Does it make sense? But understand that your pin 21 to your pin 28 fall under what we call port B. Because in the controller, pins are arranged into ports. So your port B has 8 pins. Pin 21. Don't forget here is not connected. Pin 21 is not connected to your pin 28 and your what? Port B. So your LCD.
So 1 to 24.
So 21 was not connected, but 22 down to 28 were connected to your what? To your LCD. Does that make sense? But understand that your pin 21 to your pin 28 are your what? Port B pins. Port B pins. You get it? So you can call it. Let me write this. So this one is going to be your port B bit 1, port B bit 2, port B bit 3, port B bit 4, bit 5, bit 6, bit 7, bit. Sorry, bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7.
7.
So bit 0, look at it. Arrow B0, arrow B1, arrow B2, arrow B3, arrow B4, arrow B5, arrow B6, arrow B7 will be port B bit 0, port B bit 1, port B bit 2, port B bit 3, port B bit 4, port B bit 5, port B bit 6, port B bit 7. Which, of course,
Is it bits or saying?
yeah, bits, dots. Which is pin 21, pin 22, pin 23, pin 24, pin 25, pin 26, pin 27, and pin 28. Does it make sense? It's clear? So that is how the LCD was connected to microcontroller. So, can I continue? So what we have left to talk about will then be the microphone. The mic has 2 pins, or 4 pins, 3 pins actually. It has where you put the positive voltage, it has where you put the negative voltage, and it has the signal out. Now the microphone we are using is a condensed mic module that is bought in the market. What I will do is that later in the day, I'm going to give you I'm going to go online and get you the schematic caption. What's actually in it? The microphone with its circuitries. It has a preamplifier already on board. It has a preamplifier already on board. So what happens is that it receives sound, or it picks up sound or noise through this microphone, and then I believe it has already amplifiers on board. It has LEDs there that comes on. It has all of its processes and all of its components there, so that at the end of the day you have an analog output. So you have just 3 pins: ground, VDD, and out. Are you with me? So 3 pins. Positive. For the positive, this pin goes to what? To your VDD also. This goes to your VSS. And then this out goes to your microcontroller. Now this out is analog. Analog. What it means is that based on the sound that it receives, it gives you an analog output. Analog output will be something that keeps doing like this. Are you with me? Now, there is a port on the microcontroller that is used for analog input. You can't just connect any analog signal into the microcontrollers to any pin on the microcontroller. There are some pins and ports dedicated for that. For any microcontroller that allows analog input, you will likely find those pins on your port A. So you're going to find those pins on your ports. Let me ignore this. So let me call this port B. Don't forget, just the way you have port B, you're also going to have ROA0, ROA1, ROA2, ROA3, ROA4, and ROA5, which should be port A with 0, port A with 1. Are you following? Port A with 2. Now, all the pins of the microcontroller can be used for digital input and output. But you see, the pins on the port A can also be used for analog input alone. You can't use port B for analog input. You can't use port C for analog input. You can only use port A. For your project, we have used ROA0, which is the pin 2. That ROA0 is also your analog channel 0. So that is what is connected to the Vout. Are you there? So that as the microphone picks up the sound, and then it gives an analog output. The analog output that it gets is then fed into the ADC of the microcontroller. Then codes are done to process that and then convert that analog values to what? To binary values. Does it make sense? So that in a simple form is the electronic aspect of the product. Now don't forget, on it is the microphone itself, on this board is the preamp stage. What is not on this board is the fatal point. And I mean, from all that I've gathered 2 weeks ago, starting this year, we have a problem with that fatal stage.